So we have about a minute. Are there any questions? We've talked about the exam a couple times. Just looking at the upcoming schedule. Homework 3 is due on Monday, and then the exam will be the following Friday. No class that day. I'll just run down the basics again real quick. I normally talk about the exams the week before. It'll be on WebAssign, 25 questions, multiple choice. Will appear at noon. Will be due at noon the following day, 24 hours. It's not timed, so you can come and go. It's open book and notes. Though I encourage you to put together a sheet of notes ahead of time. I think that really helps to consolidate all the information, to learn what's going on. Study the homeworks and the answer keys. Be sure to press that answer key button to look at the solutions. Even if you got it right, you may have gotten it right, not for the right reasons. So check that out. Warm-up questions I'll post after class on Monday. The ones we've been doing in class, and there are a few that I skipped over due to lack of time. They'll be in there as well, and so you can study from those as well. And I think that's it. All that makes sense. Any questions about any of that? Okay, that's what's coming up. And on Monday, we'll begin lesson 4. So Monday and Wednesday will be lesson 4. That will not be on the exam, but we will make use of the time and just plow forward. Okay, so there are no questions. Then first up, we have our warm-up question, just one today. And let me read through it. So a hydrogen atom has a single electron in the ground state, so the low energy configuration. And that electron is jostled by another nearby atom, just bumps into it, or the other one bumps into it. The energy associated with this jostling would be enough to push the electron to a greater average distance from the nucleus. To move away from a charge, you have to inject energy, just like to move a rocket ship away from the Earth. That has to, you have to give it energy, or a satellite or something like that. And let's say the energy of this jostling is enough to send it about halfway between the ground state and the first excited state. In that case, what happens? Either 1, the electron stays in the ground state, the same average distance from the nucleus. In other words, that energy is not accepted. 2, the electron moves to this distance, partway between the ground state and the first excited state, and then exists there. Or 3, the electron moves to the first excited state, which is about twice as far away. So 1, 2, or 3. And we got 56 responses. I'll give you another 20 seconds or so to put your answer in there. Can we break 60? There, okay. Show values, 6, that's creative. And show histogram, 1, 2, 3. Most of you selected 1, and that is the correct answer. So as we established last time, the electron travels not as a particle, so it's not like a planet orbiting a star. It's, we often draw the picture of atoms that way, but that's not what's going on. They're traveling as waves, and waves are kind of everywhere with different probabilities. Waves can constructively interfere in some places and destructively interfere at other places. And with electrons around nuclei, they constructively interfere, as we showed, at particular radii. So those are the only places the electron can really be. And if we give it enough energy to move halfway between 2 orbitals, that's a region of destructive interference, and the electron simply can't exist there. So that energy will not be accepted. It will stay in the ground state. And as we'll see, if we haven't figured this out already, this is why we have absorption line spectra. We have atoms there, we send a continuous spectrum of light through it, all the different energies. Only certain energies will be absorbed. Those are the energies that correspond to transitioning from state to state to state. But what this addresses is the stability. Remember, the two things that Bohr insisted upon is, one, the orbits are quantized, and he got that by making the electrons travel as waves, and that they're stable against jostling, because they're not like solar systems, which are spaced really far apart in the universe. Atoms are right up against each other, always disturbing each other. And if they were classical systems, particles orbiting like planets around stars, the electrons would just get scattered out once you start jostling. But instead they're stable because you can jostle it with a little bit of energy and it's not going to move. It will reject that energy. Okay, that's the point of that. All right, so we left off here, again with the quantum, the wave-like picture of the atom. But these are complicated diagrams to draw, so we're going to go back to drawing them as what appear to be little planets going around stars. Just keep in your back of your mind or the front of your mind that that's not really what's going on. This is a wave phenomenon. This is quantum mechanics. Behavior is a little non-traditional. But in terms of diagrams, it's just easier to draw it this way. So, yeah, let's touch on the absorption line spectra, that they're just lines. So if the wave is only constructive at certain distances, there are only certain places that you can be. And so let's say we have an electron down in the ground state, and instead of a jostling, like we saw in the warm-up question, let's say an ultraviolet photon comes in and strikes the electron. Let's say it's just the right amount of energy to move it up from that ground state to the first excited state. Well, then you get that absorption spectrum. If it's just the right energy, it will be absorbed. And hence, here we have our continuum light going through this cloud. And if it's just the right energy, it transition from the ground state to the first excited state, or from any state that the electron's in to a state higher up, that energy is absorbed, and that's why we don't see lines there. And then you have at least some of those atoms in that cloud in an excited state. Maybe most of the cloud is still in the ground state, but the subset that is in the excited state, this is a sufficiently hot or heated gas, and those electrons will come back down. And it's a random process. They don't come back down automatically. It's quantum mechanical. You know, what are the odds of the wave actually being able to transition to the other wave and release this light? Their whole advanced courses in figuring out these time scales, these probabilities and these time scales. But the fact is, after enough time, it will transition back down and re-release that photon. Except now it'll be released in some random direction. So before, light is going through the cloud and it's being absorbed, but then that light's re-emitted in all possible directions. So if we look at the cloud from any other direction, we'll see that re-emitted light. Basically, the same lines that were absorbed are now coming out in other directions. They also come out in this direction, but they're barely noticeable. Like all the light's absorbed and then a smidgen is re-emitted in this direction and the rest is re-emitted in other directions. So from these other directions, we see emission line spectra. Now, actually, let's go back to this figure and just write a few things down. So what we know is that the orbitals, the orbitals, that's what we call them since they're waves instead of particles, orbitals instead of orbits. The orbitals are quantized. We figured that out now because it's a wave. There's only certain distances, certain radii that the electron can be. The electron wave can be for constructive interference. And what this means is that the energy is quantized, because it's just like a rocket ship. If I want to blast off the Earth and go up to a certain level, it takes a certain amount of energy. If I want to go from there to the higher up, it takes a certain amount of energy. So pulling the electron away from the charge takes certain energy, but if you can only be at certain places, then there are only certain energies that can be absorbed. So the energy is quantized. And here's our equation. You know, the energy of a wave is proportional to its frequency. With light, the constant proportionality is Planck's constant. But the point is that's just a constant. The energies are quantized. The frequencies are quantized. So frequency quantized. And we can also state this in terms of wavelengths. We know that wavelength times frequency is the speed of light. So frequency, so wavelength is...
Dr. Reichart?
Yes.
Can you explain the idea of quantized again? I'm sorry.
The quantized means you can only be at certain distances from the nucleus. Because it's traveling as a wave. The wave, it's waving its way around as it goes. I drew it last time. I'm not sure where that is, but I'll just throw my personal notes up under the dot cam. If you have an integer number of wavelengths going around, it comes back and it's on top of itself. And so it will constructively interfere, and that is a place the electron or the electron wave can be. If you're a little bit farther away, this circle is a greater radius. Here you can see 1 electron wave, 2, 3, and in this case it's a half. So when it comes back around, it's opposite. It's destructively interfering with itself, canceling itself out. That means the wave has no probability of existing at this radius. So there are only certain radii where you get that constructive interference, where 1 wavelength, or 2, or 3, or 4, etc., wrap completely around the orbit and back on top of itself.
Thank you.
Yep. It's all because it's a wave. If it was traveling as a particle, it could orbit at any distance it wanted, just like planets or asteroids or comets or dust or spacecraft going around the sun. Since it's a wave, you have these quantized orbitals, quantized distances from the nucleus. That means quantized energies to transition between these quantized distances. By this equation, it means quantized frequencies. By this equation, it means that the wavelength is quantized. So again, when we look at figures like this, here you can see specific frequencies, wavelengths, energies, however you want to refer to it, have been absorbed and specific ones emitted. And it can get more complicated. So here's a higher energy photon striking an electron in the ground state, enough to boost it up to the second excited state. And then when it decays, it can decay 2 different ways. There are different probabilities. It's a probabilistic process. It can come straight back down to the ground state, releasing the exact same photon except in some random direction. Or it can hop down in 2 steps, a small jump and then another small jump. So we can either get a high energy ultraviolet photon, or in this case, it'd be a visible photon and a lower energy ultraviolet photon. And that explains why we said the emission spectra aren't exactly the same as the absorption spectra. Same pattern, but different intensities. They can be absorbed, like here's a high energy photon being absorbed, but it could be emitted as maybe this one plus this one. So you have different intensities of lines in emission than absorption. So that explains that. Here's the same thing presented a little differently, and this will introduce some terminology that will help with homework and exam questions. And here we're seeing the transitions. These are all transitions to or from the ground state. Maybe it starts, the ground state moves up, or it's in higher states, and these are transitions back to the ground state. Here's to and from the first excited state, to and from the second excited state. Each of these groups of transitions we call a series. So let's get a fresh page here. And in particular, we're focusing in on hydrogen now. We've been kind of gravitating that way in our figures, but let's just start with hydrogen because it's the simplest atom. 1 proton, 1 electron. Sorry, DocCam, hydrogen atom. And we're going to introduce the idea of series and the different conditions under which you see different series. So let's start with the Lyman series. And these all these are all transitions to and from the ground state. So the transition from the ground state to the first excited state, that takes the most energy out of all these, any transition from one level to one level up. Here you're very close to the proton, so it takes a lot of energy to pull it that first distance. It takes less energy to pull it the next distance and less beyond that and beyond that. Just like a rocket ship, most of the energy is getting into near Earth orbit, and then it's less and less for each equal distance you go. Anyway, it's a lot of energy. So high energy is a high frequency, which is a short wavelength, and you can see this is a short wavelength, 122 nanometers. And just to remind you, visible light is visible, runs from 400 nanometers to 700 nanometers, where 700 is the red side, 400 is the blue or violet side. It's technically violet, though often we just say red to blue, blue to red, red shifts, blue shifts, but violet's actually the limit there. So this first one is shorter than 400, so it's in what type of light is this? Well, I guess the answer is right here. It's silly to ask a question when the answer is presented. Ultraviolet, being shorter than 400 nanometers, this is an ultraviolet photon. I want to go from the ground higher up, that's more energy. So shorter wavelength, higher frequency, shorter wavelength. As I go to higher and higher energy transitions, here to here, here to here, here to here, it's shorter and shorter and shorter wavelengths. And so the first transition, we call that Lyman alpha. That's the one at 122 nanometers.
I can't see your screen.
Thank you. The second one is called Lyman beta, Lyman gamma, delta, epsilon, and so forth. Just terminology. So the first one here in the Lyman sequence is Lyman alpha, Lyman beta, Lyman gamma, Lyman delta, and these are all in the ultraviolet. The Lyman series is in the ultraviolet. Now the next series up is all transitions to and from the first excited state. And before we can talk about this series, we have to talk about how the electrons get up there. And maybe you had electrons in the ground state and it absorbed the right type of ultraviolet photon and now it's up there. But normally, if you have like a cloud of gas, you can knock one or two or a small fraction of the electrons up to a higher state by absorbing. But if you want to get all the electrons up to that higher state, the primary way this is done is not through absorption of light, but through collisional excitation. Let me write that term down. This is, if the gas is hot, the particles will be bouncing into each other. If it's hot enough, they'll bounce into each other with enough oomph and enough energy that the electrons can absorb that energy and move up to the higher state. So, here we have two hydrogen atoms in the ground state. They bounce off each other with enough energy that one of the electrons finds itself in the first excited state. And if you make the gas hot enough, then pretty much all the electrons will be in that first excited state. So imagine a gas that's, if it's cool, a cool gas, you're going to be talking about Lyman absorption. But if it's a 10,000 degree Kelvin gas, then through collisional excitation, most electrons will already be in that first excited state. Then imagine the light going through. Imagine you have a gas that's already 10,000 degrees. Maybe it's a cloud out in space. Maybe it's the upper layer of a star. And then the light from below passes through this gas. What you will then get is the Balmer series, because the electrons are already starting here. And so you'll have some of those electrons transition from the first to the second excited state. Not these numbers N, they don't match with the names, as I mentioned last time. First excited state to the third, first to fourth, first to fifth excited state. and that's the Balmer series. And these transitions take less energy because you're already farther from the charge. It's like that rocket, it's already farther out in space. And so it takes less energy. These are, since it's lower energies, it's lower frequencies, which are longer wavelengths. And so you can see here, 656, that's pretty close to red. So 656 is a red photon. And then these are all close to 400, that's on the blue side. And technically, if you keep going, it does move into the ultraviolet, but at least for these primary lines, they're visible. So let's write down the Balmer sequence. So this is the Balmer series. It's primarily in the visible part of the spectrum. And these are to and from the first excited state. And we call these H alpha, H beta, H gamma. Instead of B for Balmer, we call them H because they were discovered first, being in the visible part of the spectrum. You know, our eyes work there, so we were able to find these lines first, and we just labeled H for hydrogen. That's really the Balmer series. And you've seen these before. Here they are in absorption. Here's that one red line, and then the converging sequence towards the blue, H alpha, H beta, H gamma, H delta. And here it is in emission. And remember, we looked at hydrogen in emission using a grating to disperse it and see the spectrum. There is one red line and a converging series towards the blue-violet side of the spectrum. Okay, let's take this one more level. I'm out of, well, I have a little bit more space here. Let me just, I'll put it in down here. So imagine you had a gas that's even hotter, 25,000 Kelvin gas. Then through, again, collisional excitation, most of the electrons will be pushed up to the second excited state. And that's just from them bumping into each other. Then imagine light passing through a 25,000 Kelvin gas, and you'll have the Paschen series. And you can see it here. These are transitions to and from the second excited state, and the wavelengths are even longer since they're even lower energy transitions. They're longer than 700, so it's beyond the red. They'll be in the infrared right here. So the Paschen series is primarily in the infrared, and we call these, you know, Paschen alpha, Paschen beta, PA for Paschen, Paschen gamma, etc. And these are transitions to and from the second excited state. And you can keep playing this game. Transitions to and from the third excited state, that's called the bracket series. To and from the fourth is the Fund series, PFUN with the silent P. After that, the Humphreys series, and after that, they don't even have names. We just keep track of the number of the transition. Okay, and all those would be farther and farther into the infrared. And so what you're seeing here is, you know, the spectrum we see tells us composition. Like if we see a hydrogen series, we know it's hydrogen, but also which hydrogen series we see tells us the temperature. Here's another way to look at the exact same plot. This is an energy level diagram. Here we have the ground state, the first excited, second excited, so forth and so on. And here are all the transitions to and from the ground state. You see that biggest transition is that first one. It takes the most energy to get away from that initial distance away from the proton. And the farther away you are, the less energy it takes to get the same distance farther out. And these aren't distances in space. These are distances in energy. So you see less and less energy to make these transitions. Here are the transitions for the Balmer series, the Paschen series. It comes out in the ultraviolet, visible, infrared. And so going up is absorption, coming down is emission. And if you have enough energy, you can escape completely. You can ionize. For hydrogen, we use this Often with atomic transitions, we use this energy unit called electron volt. You don't really need to know what it means. You may have seen it in high school chemistry, but in this scale, 13.6 lets you escape. And it's 10.2 to transition from the ground to the first excited state. So not much more energy to escape completely. And we call that ionization. Okay, a specific example. And this pertains to one of the homework questions, homework question 8, I think. So this is the solar spectrum. Imagine taking the sun's light and dispersing it through a prism. This is really high resolution. So it'd be so long it wouldn't fit on my screen, so I've chopped it into pieces and layered it. So it's like a carriage return as you're reading. This part connects to this, then that part connects to that. But imagine it's one long spectrum. And we see lots and lots of absorption lines here. A lot of them are iron, potassium, things of that nature. Oxygen, nitrogen, some of that's from Earth's atmosphere. But a lot of the iron, potassium, and these other things, it's the solar atmosphere. But the sun's not made primarily of iron and potassium. It's, like most stars, made almost completely of hydrogen and helium. Yet, here, this is the visible part of the spectrum, and we look, and there are some hydrogen lines. There are some Balmer lines. Like there's Balmer alpha. I think that's Balmer beta. Maybe that is right there. And then Balmer gamma, Balmer delta down here somewhere. But most of the lines are not hydrogen. And for the thing's made primarily of hydrogen, and given that the hydrogen lines are really weak. So why is that? Why don't we see a strong hydrogen series when looking at the solar spectrum in the visible? I'll throw that to you. You want to guess?
Does it have to do with the temperature?
Yes, it has to do with the temperature.
The sun is too cold.
Yes, that's right. The sun's surface temperature is 5,800 Kelvin, about 6,000 Kelvin, which to us seems hot, but it's too cold for the Balmer series. And the Balmer series we see in the visible. Now back to this plot here. If we're less than 10,000 degrees, most of the electrons are in the ground state. Even though that burn you, it's in the ground state. And so you're going to get a Lyman series. And that will appear in the ultraviolet. So if we were to continue this down beyond the bottom of the plot, and we do have ultraviolet detectors and can do this, the human eye can't see it, but we can detect it and convert it into something we do see, then you see whopping strong, huge hydrogen absorption lines, which makes sense because the sun is primarily hydrogen. But if you look in the visible, and if you don't understand what's going on, you may say, oh, the sun's made of barely any hydrogen at all. It must be a ball of iron and potassium. And it's not. Iron and potassium, they have, the lines are fairly strong in the visible, but most of the lines are hydrogen, helium lines out in the ultraviolet for this temperature. Now, not all stars are that temperature. Here are, and this is some Astro 102 stuff, here are a bunch of stellar spectra for stars of different surface temperatures. Here's the sun. The sun's a G5 star, so pretty close to this. We're a tad bit hotter, but we're a G5. And here's H alpha, H beta, H gamma, and so forth. And if you look on this line, we see hardly any Balmer emission. Here's H beta, H gamma, just we're too cool. The electrons are in the ground state. But if we go up here to stars with surfaces that are 10,000 degrees, just through collisional excitation, the atoms bumping into each other, all the electrons start in the first excited state, and then the light comes from below, generated in the core through nuclear fusion, works its way out. It can take hundreds of thousands of years for light to bounce its way out of the star. But then it passes through this gas, and there you see the Balmer sequence. And here, when you get up to 25,000 degrees or so, then you see the lines disappear again, because now the electrons are in that second excited state, and you're getting a Paschen series, which is out here in the infrared. Okay, so hopefully that gives you enough information to answer question 8. Read through all the options, and you'll see that many of them are saying the same thing in different ways. That's my hint to you. Okay, so that was hydrogen, and checking the time. We're doing good. We have about 20 minutes. Correct, yep. So that was hydrogen, which we see up here, though we looked at some other elements last time and saw that they have a different spectrum. Every element has a different spectrum. So what are the primary things responsible for these differences? Why does a helium have a different spectrum than hydrogen? Anyone want to venture some guesses?
Different number of protons.
Yep, that's the key one. So the number of protons. So let's see, we're talking about other elements. So protons, that's the first one. So here's the helium, and we have 2 protons. And so again, if you think about the gravitational analogy, that'd be like doubling the mass of the central body. Gravity would be stronger, it'd hold things in closer. The same is true. You double the charge, it's going to pull the electron in closer. The differences between the levels will now be different. And so you will have different transitions. If we look at the helium spectrum, it's not too wildly different. It's like the whole thing is shifted, at least largely. And here we have carbon with 6 charges, and so the orbitals are much closer in, so again, different transitions. So that's the primary effect. What's the secondary difference?
Well, if you have more electrons and you have them already on those different levels, is that going to affect it?
Yes, and actually in 2 ways. So I just wrote on the dot cam, number 2 is the electrons. You have more electrons, you can have more transitions. And so you can have more lines. That's one effect. And the second effect is shielding. Let me write that down. Let me write down the 2 things. You have more lines, more possible lines, and shielding. Yeah. You know, this electron could jump, this electron could jump. If you have a partially ionized atom, it changes the number of electrons and into different transitions as well. But shielding, consider this electron here. It doesn't feel the full impact of the nucleus because there's some negative charges between it. So it's feeling the positive charges, but the negative charge is not attractive but repulsive. It kind of cancels out the nucleus. So these outer ones are feeling less of a charge than the inner ones. The point is it gets really complicated once you start adding all these particles. And so you're going to have much greater variation in spectral signature. So every single element on the periodic table will have a unique spectrum. And actually here they are for the visible part anyway. Some of them are hard to see. I guess there are lines for hydrogen, helium. I can barely see them. Some are easier. Let's see, I'm looking for neon because that was one we looked at the other day. I should probably know where it is in the periodic table.
Below helium.
Yeah, of course. And yeah, and here you see, it's maybe not coming through very well, but all the red lines. You may remember that from last time. Neon had a bunch of red lines. Anyway, each element has a unique spectrum. And so again, it's very powerful. We can figure out what these spectra look like in the lab, not just in the visible, but in the infrared, in the ultraviolet. Then we can look in space and disentangle. We always get them all merged together on top of each other, but we have good software. We can disentangle them and figure out compositions and, of course, temperatures. Different temperatures will show different series. So just summarizing, I think you get all this at this point, but we'd introduced Kirchhoff's laws as empirical laws, but now that we've explained how atoms work, it all makes sense. You know, here we have a thermal distribution, so we get a continuous spectrum. If there's any gas in between, either like in space in between or in this gas here in the solar atmosphere or in Earth's atmosphere on the receiving side, that gas is full of atoms. The atoms have electrons that can only exist at particular levels. So you get discrete absorption, you get line absorption, and then that subset of the particles that went to that higher state, and before they went, they were sufficiently cool. Sufficiently meaning they're in a low enough state that they can jump up to a higher state. Now these ones that are in the higher state, they're sufficiently hot, meaning they can jump down to a lower state, re-emitting that line emission. So same patterns, but in all directions. Okay, so Kirchhoff's laws explained in terms of atomic theory. Questions about any of that before we do the last bit? Okay, so one more thing, and in the textbook, this is chapters 3 and 4, and I think the Doppler effect is covered at the end of 3, and I skipped over it, and I'm coming back and doing it now. So this last bit here, actually I can probably still make use of this page. Slide it up a little bit, is the Doppler effect. And it's yet just one more way that we can get information out of light. The whole goal of this lesson is to extract physically useful information from light by taking advantage of its properties, understanding them and taking advantage of them. So the Doppler effect. Well, so far we've learned how to use the spectrum to figure out compositions and temperatures. Now we're going to learn how to figure out motions. These aren't the total velocity, but the line of sight motion, the component of the motion that's either towards us or away from us. This is something you can figure out since light is a wave. Now, one example, and it works for any wave, sound waves. Have you heard a siren go by and the pitch change? With sound, the frequency manifests itself as a pitch. With light, it manifests itself as a color. But with sound, you've heard it where it goes, I hope you got that because I only do that once. So yeah, the change in pitch when it passes you, from when it's coming towards you to when it's moving away. And it's because when it's coming towards you, those waves get compressed, and when it's moving away, those waves are stretched out, and we'll go through that in some detail, but that changes the pitch. In case of light, changes the color. If you haven't heard it, and you don't trust my verbal simulation of it, we'll do a little demo here. And this works in the classroom. I don't know how well it will work here because the classroom is really large. This is a small room, and the sound waves may bounce off all the walls, and there's no way I guess I could have tested this and recorded it. But what I have here is a noisemaker, single frequency, and I'm going to rotate it towards the computer's microphone. Whoa, yep, small room. So do you hear the pitch changing up, down? I'll assume that's a yes. Actually, I'll stop for a second, take a look at your faces. Did you hear the change in pitch? Okay, now I'm going to do it the other way, not moving towards you or away from you. See, when I did that, I didn't really hear a change in pitch because it wasn't moving towards or away from me. It's perpendicular to me. Now, I did hear it bouncing off the walls because I'm in a small room. And you may hear it bouncing off the walls as well. But if I do it perpendicular, you should hear less of a variation. Actually, let me shorten it a little bit. So I don't know. Did you hear less of a variation? It may have been hard.
Yes.
Because
Yeah, we did.
okay, cool. So that kind of worked. And again, that's sound waves. But the same holds true with light waves. And so here's a diagram. Here we have a source of light. And in this case, it's not moving. And then we have two observers. Depicted here as two space shuttles. So you know it's an old figure. But two observers on either side of this light source. And these lines are the crests of the waves. So at time 1, it emitted, and all the way at time 5, that crest made it out to here. At time 2, it emitted the next crest, and that's now made it out to here. The one at time 3 has made it this far, 4, and then 5. And since it's not moving, they're spaced the same as they were emitted. And so the observers will receive that light at the same wavelengths that they were emitted. Now, if your source is moving, and this also works if the source is stationary and the observer is moving, according to Einstein, no one knows who's actually at rest, right? This is all about relative motion. But as drawn here, let's say the observers are stationary and the source of light is moving. So the light that was emitted at time 1 is all the way out here, centered on the point that it was emitted. The light that was emitted at time 2 is again out here, centered on where it was when it was emitted, which is shifted because it's moving. Time 3 is centered here, time 4 is centered here. So since the source is moving, the waves get compressed in the direction of motion. Shorter wavelengths will be received, which means higher frequencies. And for light, that's a bluer color. For sound, that's a higher pitch. In the other direction, they get stretched out. And so longer wavelengths, lower frequencies, redder color, and with sound, a lower pitch. Let's say I think I have a web simulation here of this. So you can just Google and find these things. Every time I teach the class, it's usually a different one that comes up here. There we go. And let's see, I'm starting it. And here we have a stationary source. Here we have the observer receiving them at the same rate that they're being emitted. Now I can increase the velocity of the source. And you see the waves are compressed in the direction of motion. So right there. So I did do it again. The lower pitch. Of course, with light, it'd be a change in color. Now I could make it even faster. Let me try to get it just at the sound speed. This particular simulation is with sound. And so here we have an object moving at the sound speed. Now I'll just reset it and have it do it again. So you see the waves all pile up. You have a shock wave forming. And with light, you can never go faster than the speed of light. So that's as much compression as you can get. But with sound, you can go faster than the speed of sound. That's, Mach 1's the speed of sound. We have planes that go much faster. So I'll increase the speed even more. And you see, you get this conical pattern. And on the edge, they really get piled up on that cone. So if you're down here, you may see the plane fly overhead, not really hear anything, and then you hear boom, all the sound at once, and that's a sonic boom. Have you ever heard a sonic boom before? Sometimes a plane will be flying supersonic, and particularly at air shows and things like that. Or if you live near a military base, you may get that, but it can be quite startling. The air is really compressed and it hits your eardrum all at once.
I live in Fort Bragg and I hear them all the time.
All the time, yep.
Dr. Reichart?
Yes.
If you had a plane moving at precisely Mach 1 and then relative to you, the sound waves weren't moving, what would you hear?
So if it's moving at Mach 1, that was somewhere around here, you still hear that boom. There is a compression. It's just not quite that conical shape. Basically, you hear it when it's overhead. Let me restart one more time. Suppose I'm standing down here. I see it. It's overhead. Boom. I hear it there. And the waves are a little bit stretched out, but there's a lot of compression still.
If it was moving precisely Mach 1 and like all the sound waves behind it were moving Mach 1, then wouldn't you only hear the initial boom and that was it?
Oh, after the
no
boom.
Other waves would hit you?
Yeah, after the boom, you don't really hear that much, right? You get all the waves at once, particularly if you go above. You get all the waves at once and then it's just quiet. Just the tail ends of the waves there. So, think back to the figures. Okay. Oh, yeah. And here's an example. When planes do cross the sound barrier, you can see the cone just for an instant, for about a second or two. It has something to do with, it becomes opaque, and then it becomes transparent. And I looked it up once, but I forget why you have that moment of opacity before it becomes transparent. But during that moment of opacity, you can see the cone. But again, with light, that never happens. You can't go faster than the speed of light. You just get compression.
Professor?
Yeah, go ahead.
Does the sound barrier actually create resistance, or I don't like?
does it create resistance? It is, I mean, it's like you would feel it. Your eardrums feel it. With playing even way far away, your eardrums feel it. If you're close, probably your whole body would feel it. It is a shock wave, kind of like an explosion. And a lot of explosions, the material is being thrown out faster than the sound speed. And so you feel it. I can attest to that personally, actually. Some of you have looked up my history at the university over the past couple of years. But I don't know, does that answer the question?
Yeah, I guess I just never really understood like why there's actually like the sound barrier that gets broken through.
Yeah, it's, I mean, all waves have a certain speed, and it is possible to travel faster than the wave speed for anything but light. And so once you cross that speed, all the waves pile up on each other. If you're in the ocean and you're being hit wave after wave after wave, you feel that. Now imagine being hit by all the waves at once, and that's a shock wave.
Dr. Reichert, by the way, Google says that it's moisture being trapped in between the high pressure airwaves.
Moisture, yep. And that must dissipate quickly.
Yeah, it's the pressure between the sonic boom and the airplane wing that traps the moisture, condenses it, you can see it, and then it dissipates.
Okay, cool. So here's the example with light. Here's our bomber emission spectrum with the red and then the converging series towards the violet. And you can see, even for high speeds, it's a small effect. Here's at rest. These are the wavelengths that we expect at rest from measuring it in the lab. Here, it's moving away 300 kilometers per second, which sounds pretty fast. That's per second, not per hour. It's actually a typical speed of things in space, like astronomical objects. And it changes at just less than a nanometer. But remember, the speed of light is 300,000 kilometers per second. So this is 1,000th the speed of light, so it's just a small change. And they all have the same fractional change. If it's moving away, then the waves are stretched out, so they're longer. Here we have another example, something approaching us at 600 kilometers per second, and so the shift is towards the blue. So if it's moving away, we call it a red shift. If it's moving towards us, it's a blue shift. And again, it's a small amount because the speed is much less than the speed of the wave. So let's write down the equation. The dot cam. When I did my spinning demo before, was I upside down?
Yep.
I forgot to flip it before. Okay, still, it doesn't matter. We were listening, not watching. And okay, so here's the equation. The change in wavelength divided by the emitted wavelength, it's just equal to the speed of the object divided by the speed of the wave, which for light is c. So often the way this works is astronomers will measure that shift in wavelength, which we see here, divide by the emitted wavelength. For example, maybe we measure 655 when we know it should be 656.3. So the difference there is 1.3 nanometers. We divide by 656.3 because that's what it was emitted at. And that small ratio is the difference between the velocity of the object and the speed of light. You just multiply by the speed of light and you have the velocity of the object. Or you can see it in reverse, where I give you, like I think in the homework, I give you the speed of the object and I ask how much is the shift, or what is the observed wavelength. The observed wavelength is the emitted wavelength plus or minus the shift in wavelength. And if it's plus, is that moving away or towards?
Away. Because
Yes, it's moving away from us, we add the shift. So this is a red shift. If it's moving towards us, we subtract it. We call that a blue shift. Okay. So that should help you do the last question in the homework. Now the final bit takes about 5 minutes, and I'm not going to make you wait. Instead, I'm going to assign a video, but just briefly tell you what it is. There's one more piece of information that we can get, and that's out of the width of the line. If we take this line and zoom in, it has a width. And what that width is telling us about, maybe I'll do it real quick and then you can watch the video for more information, is internal motions. Suppose we have a cloud of gas and it's moving towards us, so everything's blue shifted. But in the cloud, some particles are moving towards us faster and some a little bit slower because the thermal motions, they're bouncing around. So at any given time, half will be moving faster, half will be moving slower. And so that broadens the line. So by zooming in and measuring the width of the line, which we can do, we can figure out how hot the gas is. Or maybe it's not a cloud of gas with random motions. Maybe it's a star with ordered motions, where one side's moving towards us, one side's moving away, but we can't distinguish it. It's all blurred together on the sky because it's so far away. So we just see a broad line where one side corresponds to the side that's moving towards us, one that's the side that's moving away. So it's a little context specific. If I know I'm looking at a cloud of gas, I can use the width to measure temperature. If I know I'm looking at a rotating star, I can use the width to measure the rotation speed. So just to summarize, I did that very quick, but I think I hit the main points. Let's summarize everything we can learn in a table here. We learned that if you have an object emitting thermally from the peak, we can figure out the temperature. That's Wien's law. Also the overall level, we can figure out the temperature. That's Stephan's law. By looking at the lines, we can figure out composition and temperature, whether it's an emission or absorption. By looking at the line shift, if it shifted towards us or away from us, we can figure out the line of sight velocity. And by looking at the width of the line, we can figure out even more things: temperature, rotational motion, turbulent, random motion, other things we didn't even talk about, the density of the gas, the magnetic fields in the gas. Some of that's Astor 102 material. But this is the last slide for the unit, and the point is, by taking the spectrum, we can learn a lot more about what's really going on than just by taking a picture. Okay, that's the end of lesson 3. I'll stick around for questions.
Could you show the equation for the wavelength, the observed wavelength equals the, that.
Yep, there you go. And I think the one in the homework's designed like this. I've given you the speed. You'll divide by the speed of light and figure out the shift in wavelength. And then you have to figure out whether to add it or subtract it, depending on whether the object's moving towards or away.
Dr. Riker?
Yeah.
This is kind of unrelated to the course. It's more with the lab. I'm like in the process of moving right now, and I haven't been able to start the second lab, but will I have like enough time starting Monday of next week before the lab is due to start and finish it?
Yeah, it's not due till Friday of next week, right?
Yes.
Same day as the exam, unfortunately.
Mm-hmm.
Is that right? Lab 2 is Friday of next week?
Yes.
That's right.
But yeah, you can get through it pretty quickly. When
Okay.
we're not doing COVID, we do a different version of that lab using globes and lights, and you do the measurements on the globe instead of using stellarium. And that takes 2 weeks to do. But the stellarium version you can do pretty quickly. I wouldn't wait to the last minute with any of the labs.
Mm-hmm.
You could do it in a day if you want to.
Okay. Thank you.
Sure.
Dr. Riker,
Yeah.
are both chapter 3 and 4 from the textbook going to be on the test?
Yes. 1,
Okay.
2, 3, 4.
Dr. Reichardt,
Yes.
can you explain the 2 reasons as to why the number of electrons causes spectrums to be different?
Yeah, the first one's pretty simple. If you have a lot of electrons, you have a lot of possible transistors. So the more electrons you have all sorts of different combinations. Maybe one has moved up to a higher level, creating space for a lower one lower down to move up to that level. You just have more possibilities than in the hydrogen atom where it's just one electron. So more electrons, more lines. And then the second one is shielding. So the inner electron shields some of the charge of the nucleus to the outer electrons. This outer electron is not going to feel all 6 positive charges. At any given time, likely one of these 2 inner electrons will be between it, canceling it out somewhat.
Okay, thank you.
Sure.
Can you go to your first paper really quick? I just missed a quick equation on the notes.
This one?
No, the one with the orbitals of electrons quantified.
This page here?
I think so, yeah.
Or no, it was this one. This here?
Yeah, thank you.
The focus.
Can you put up the images of the series, the one that also displays the energies that are required to boost it from each state?
Let's see. This one.
Yes, thank you.
And all of the slides are linked in the WebAssign announcement area as well.
Thank you, Professor.